Assalamualaikum and morning all.
Waalaikumsalam, madam.
Alright, today we continue our second last chapter, which is Faraday's law. So ignore here, it stated chapter 9. So it should be chapter 3 in your syllabus. Okay, so before this, earlier we only concentrate on, in chapter 1, we concentrate on electrostatic. Okay, in electrostatic, we learn about this static charge, and we have this electric field intensity E, and also we have this electric flux density D. All right, and then next we move on to this what we call as magnetostatic. So in magnetostatic, we learn about this H, which is the electric field, which is the current field intensity, and we have this current flux density with B. Okay, and then this for the magnetostatic, we are dealing with this charge that move with the constant velocity. Okay, so we know that electrostatic is a static charge, and then we have a charge with a constant velocity. All right, and now today we will learn about this moving with time varying. Okay, and instead of if we have before this just x, y, and z, or for the magnetostatic x, y, and z, and now we have x, y, z, and t because we are considering the time varying fields. Okay. All right. So in this chapter, we will learn about the Faraday law, and at the last part, we will include, or we will see the Maxwell equation for the whole electromagnetic causes. All right. Okay, so for the Faraday's law, okay, so Faraday is electromagnetic induction law. Okay, can defined by electromagnetic induction law. So it's a basic law of electromagnetism describing how a magnetic field would interact with an electrical circuit in order to generate an electromotive force. So we will see how this magnetic field in an electrical circuit that can generate electromotive force ataupun voltage. And this voltage is what we call as the electromotive force voltage. And this effect is what we call as the electromagnetic inductions. All right. So if you look figure here, this is the Faraday's experiments. Okay. So there are three steps in the Faraday's experiment. If you can see here, the first one, if the magnet moves towards the loop, so this guy over here is holding a magnet. If the magnet is moved towards the loop, and this is the loop, okay, and this loop is connected to an ammeter, okay, in order for us to see if there's any current or no current inside this circuit. Okay, so if this guy over here move this magnet towards the loop, all right, and this ammeter will show a current, so it will point to the right, meaning that it shows there is a current inside this circuit, okay, induced in this circuit due to the magnet moving to the loop of the circuit. Okay, and then this second one, when this guy is just holding the magnet without doing anything, so the magnet is not moving at all, okay, not moving to the left or to the right, it just stays static there. So the ammeter will show nothing, meaning that if this magnet is not moving, meaning there is no current will be induced inside the circuit. So there is no current showing in the ammeter punya meter here. Okay, and this one, the last one, if the magnet move away, okay, away meaning that it moves to the right side, away from this circuit, current will move also. This one, the current will also move in the opposite directions. If you look here, if we move to the left, I mean towards the loop, it will move to the right. The jarum of the ammeter will move to the right. But when we move the magnet away from the the loop, there will be a sudden magnet wheel. The magnet field, okay, will induce also the current inside here, but then the current will be flowing in the opposite way. So this will show in the ammeter where the needle of the ammeter will show to the left, meaning that it will move in the opposite directions. Okay, so that will be inside. That will be the Faraday's experiment. So from this, Faraday conclude that when the magnetic is static, so there will be no current. When it's time varying magnetic, when the magnetic we move to the left or to the right, so it means it's time varying magnetic. So it will produce a current, and in the same time it will induce a voltage. And this voltage, what we call as the electromotive force, EMF. Okay. All right. So this is all the explanations of the experiment just now. Okay, so Michael Faraday conducted the successful experiment, okay, in the year 1831, and then magnet moved towards a loop of wire, ammeter show a presence of current, and then if it's held stationary, there will be no currents, and if the magnets move away, the ammeter shows a current but in the opposite directions. If the loop is moved towards the magnet, also a current is also detected. So remember that when we have the magnet, the electric field will come out, will be produced around surrounding the magnet. So that's why when we move, the magnetic field will induce the current inside the loop. Okay. Alright, so this Faraday law state that the induced EMF ataupun VEMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. So again, the induced EMF, VEMF, okay, this induced voltage ataupun electromotive force is VEMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. So VEMF is equal to negative N d flux over dt. So how much the magnetic flux linkage times with the numbers of turns of the circuit, okay, towards the time rate ataupun the rate of change of time dt. Okay, so that will be the equations of Faraday's law, and don't forget it's have this negative over here. All right. So why is it negative over here? This is related to Lenz's law pula. Okay, so afterwards we will go through for the Lenz's law. So here, so if you look into this definition, we can see that in any closed circuit, this just mentioned here, any closed circuit. So if we look here, ni ada video, kalau saya boleh buka ya, sekejap ya. Okay, you can see. Boleh dengar ke? Dia memang tak ada suara, sorry. So you can see here, when it move the magnet towards the circuit ataupun this loop, the loop will move. Tapi when there is an open circuit, it doesn't move at all. Okay, so you can see that the loop is not moving. Bila dia masukkan dekat closed loop, okay, it will move. Alright, so you can see that. Okay, so when the loop is open, okay, macam yang tadi showed inside the video, so when the loop is open, the magnetic flow out from the circuit. So instead of the flow around the loop, dia akan flow out sebab dia ada open circuit. Alright, so the magnetic will flow out from the circuit, so that's why it will not induce the voltage and there will be no current inside the circuit at all. Alright. Okay, then we have this negative sign in the equation over here. So this negative sign indicates that the induced voltage act in such a way to oppose the flux producing it. Okay, so it indicates that the induced voltage, okay, whatever voltage yang produced inside the circuit, okay, in such a way to oppose the flux producing it. Bila kita, when there is a current inside the voltage, it will induce a magnetic field kan in the same time. So here the Lenz's law cakap, we need this negative sign. So whenever there is a induced voltage ataupun induced current inside the circuit, it will oppose the flux producing it. Maknanya dia akan menolak the flux producing it. So tak adalah bila kita ada current, so bila kita ada current akan produce magnetic flux. Bila magnetic flux is very high, dia akan induce more current inside the inside the circuit. Again, bila current tu pula tinggi, dia akan produce pula magnetic flux tinggi lagi dalam that circuit. So it will be never ending story untuk the voltage, the current and also the magnetic flux. So Lenz's law kata that will never be happen. Okay, so it's supposed that there is an amount of current produced inside the circuit with appropriate value of magnetic inside the circuit also. Okay, so Lenz's law of electromagnetic induction state that the directions of this induced current will be such that the magnetic field created by the induced current oppose the initial changing magnetic field which produce it. Okay, so to get you understand more, so we go and see this video.
So right over here, I've depicted a square loop of a conductor. Let's say it's a wire and it's stationary and it's sitting in a magnetic field. And I've drawn a few vectors that represent the magnetic field. And you can see, at least on the surface that is defined or that's contoured by the wire, that the magnetic field looks constant. So if we just had this scenario, nothing too special going on, but it becomes interesting if I were to actually change the flux going through the surface. So both of these pictures right over here, they actually show the same scenario where we have increased the flux. We have increased the flux at these points on the surface defined by the wire. At every point, the magnetic field has now gotten stronger.
Okay,
so we
they increased the flux.
The flux. So let me write that. The flux. We use the Greek letter phi to usually denote flux. The flux of the magnetic field. The flux of the magnetic field has gone up. And we know from Faraday's law that when you have a change in your flux, that's going to induce a current in the loop. And so an interesting question is, what direction is that current actually going to go in? We have two options. The current could go, let me find a nice color for the current. The current could go in the clockwise direction, or it could go in the counterclockwise direction. So which of these two do you think the current will actually go in? Well, let's think a little bit about it. We know that a current flowing through a wire actually on its own will induce a magnetic field above and beyond the magnetic field that's already there. So let's think about the type of magnetic field that this orange current would actually induce. So if it's going in the counterclockwise direction, remember we use the right hand rule. I can take my right hand, point my thumb in the direction of the current. So let me see if I can do that. So my thumb in the direction of the current, and then my hands are going to loop, or I should say my fingers are going to loop in the direction of the magnetic field. So when I do that with my right hand, so my right hand looks at something like that, thumb in the direction of the current right over here, we see that it shows a magnetic field being induced that would wrap around like that. Or if we were to show it, if we were to sample at points right on the surface, the magnetic field that would be induced would look something like this. And I'm just doing it at some sample points. So notice, it would be additive. It would be additive. Whoops. It would be additive to the existing magnetic field. In fact, it would increase the flux even more. In fact, at these points, these vectors would increase even more. These vectors, let me see if I can draw that. These vectors would increase even more. Well, what would that do? If the flux increases even more, then the current is going to increase. The current is going to increase even more, which is going to make the flux increase even more, which makes the current increase even more. And you would have this never-ending cycle where the current keeps increasing and the flux keeps increasing. And you would have this energy that's appearing out of nowhere, which would violate the law of conservation of energy. And so that's a pretty good argument for why you would not. That's a pretty good argument for why we would not expect the counterclockwise scenario. We would not want the current that's induced to induce a magnetic field that goes in the same direction as our increase in flux. So just by deductive reasoning, we know that this is going to be the scenario. And let's think about what happens here. We can do the right hand rule again. We take our right hand, point our thumb in the direction of the current, and we see if we do that with our right hand, well, now this would induce a magnetic field that would decrease the flux. So it would produce a magnetic field. The current right over here would produce a magnetic field that's going downward. The current in that direction would also, when you take your right hand and you were to put it along here, once again, if you're going in the clockwise direction over here, that too, when you do your right hand rule right over here, your fingers would coil around that way. And so once again, when you look at the surface, it would induce a magnetic field that is going in that direction. And so it would have the induced magnetic field from the induced current will go against the change in flux. And this makes sense because we won't go into this never-ending positive feedback loop where the current keeps getting stronger and stronger and the flux keeps increasing and increasing and increasing. And this idea that the orientation of the current that is induced will produce a magnetic field that counteracts the change in flux. This is Lenz's law. Lenz's law. And once again, if that wasn't true, then you would have a violation of the conservation of energy. So in general, whenever if someone says, okay, well, this is the change in flux is happening in a certain direction. Well, to think about which way the current would flow, you just have to say, well, what type of a magnetic field would each direction of the current produce? And that magnetic field should go in a direction that goes against the flux. So if the flux is increasing, the magnetic field that's induced by the induced current should make the flux then the induced magnetic field by the induced current should make the flux decrease less, or should make the flux should be additive to the flux.
Okay, so if we're following the conservations of energy, which is the right hand rule, okay, as shown in the video, so the current and the magnetic will be ever ending induced. Okay, so we don't want this uncontrolled of current and magnetic, so that's why we need to oppose the induced current, so it will reduce and control the magnetic field. Right, so by equation here we have this negative over here, right? Okay, so again, So let's say we have, this is the equations of Faraday's law just now. So assume that we have n equals to 1. So the equation will something like this, okay? So negative, instead of negative n d flux over dt, so it will be negative d flux over dt only, all right? And then we know that flux is equal to B dot ds, okay? So if we substitute this inside the equation, so the equation will be something like this, which is VEMF equals to negative D flux before, so it now become D integrations of B dot ds, okay? So differentiations and integrations B dot ds. All right, so if I look into in terms of E, we have these integrations of closed loop E dot dl, okay? If we are considering closed loop, all right, so we have this E dot dl will be equals to negative d over dt integrations of B dot ds or lux. All right. So that is the general equations for the Faraday's law. So what are the applications of the Faraday law? So we have three types of EMF, okay, motive force. So we have three types, okay. So the first one, we have this stationary loop in a time varying B, which is known as a transform. So for this one, the loop is moving instead of B, okay? So the loop will be moving and B will be static. B is the magnetic field, so the magnetic field will be static, but the loop is moving, so that's what we call as a transformer EMF. And then the second one, we have a time varying loop and a static B. Oh, saya terbalik Sorry So the first one is stationary loop ataupun the loop is not moving. Okay, again, stationary loop ataupun the loop is not moving but the time varying field. So meaning that B is moving, flux is moving. Okay, and then the second one, so the loop sekarang adalah moving. So loop will move, is static. And the third one is both moving. So loop will move and also be also. We have three. First one, static loop. We will get a transformer EMF. The second one will be the loop will move and static magnetic, that we call as the motional EMF. And the third one will be both is moving. We have moving loops and moving the magnetic field. All right, but in this course, we only cover the third one. Okay, so only two. So if you look here, this is the first one. So the first one is stationary loop in a time varying field, and this is known as a transformer EMF. Okay. So this EMF induced by the time varying current, so it will produce the time varying field in the stationary loop. So it's often referred to as a transformer EMF. Okay. And again, the equation, we will just using the general equations of the Faraday law, where we have this VEMF is equals to the flux linkage over dt and equals to negative n, the numbers of turn, the d flux over dt, or we can also write is in terms of negative n, the integrations of dB over dt, where we have this B dot ds is the flux. Okay. All right, so here if we look into the Stokes theorem, so we have these integrations of del cross E dot ds. Okay, so it will be also equals to negative dB over dt dot ds, and finally we will have these equations for the Stokes theorem. Okay, del cross E will be equals to dB over dt, and this is also part of the Maxwell equations for the time varying field. All right. Okay, so the second one, we have this what we call as the motional EMF, where we have this time varying loop and static magnetic field. So we considering a conducting loop moving with a uniform velocity. Okay, so this loop will move with the velocity of u, and then the EMF induced in the loop can be found by using these equations, where we have VEMF is equals to the integrations of closed loop U cross B. Okay, so this is cross, so U cross B dot dl. Okay, so U is the velocity, B is the flux, dot dl. dl is where is the magnetic field passing through, which the line it passing through. Okay, dl. All right. So where U cross B is defined as the motional electric field, ataupun kita panggil dia sebagai EM. Alright, and then this is called motional EMF. Alright, and then there is 3 points that you need to look into. Okay, so DL is taken along the loop, a bar that is cutting the field. So you can see that DL, what is DL? So DL we determine from the bar ataupun from the loop where it cuts the field of the magnetic field. Okay, so along the loop or bar that is cutting the field, so that will be the line. And then the second point is that the directions of the induced current is the same as this cross product. Okay, so we have this cross product, and the final answer for this cross product will have directions. Okay, and this direction will be the same. The directions of DL should be the same as the directions of your cross product. And then the limit of the integral, okay, so the limit that you need to include inside your integration afterwards. So this limit, okay, will be selected in the directions of opposite the induced currents. All right. So if let's say we have this U cross B and the directions is AX, okay. So the directions of the limit, okay, the limit will be negative AX. All right. So you can look afterwards in the example. Okay. So C, so a time varying loop area in time varying field. Okay, so we have this both moving. So when both is moving, so we have VEMF equals to sekejap. Okay, so for our syllabus, we only concentrate for the two types earlier only. Okay, so transformer and also motional EMF. All right, so we go into the example. Right, so this is example 1. So a circular loop conductor as shown in the figure lies in the Z equals to 0. So this should be 0. Okay, and then has a radius of 0.1 meters. So the radius is 0.1 and a resistance of 5 ohm. So given B is 0.2 sine 10 power of 3 T AZ, so AZ direction, so you can see that the directions of your magnetic is towards positive directions. Okay, so we have this AZ, and then determine the current determine the current induced in the loop using Faraday law. So when we have this a single line loop and then we have this magnetic field, so of course it will induce a current. So you need to find what is the value of the current induced inside this loop. Okay, so from these questions, so we need to first determine whether it is a motional ataupun it is a transformer. So if we look here, it's given B is equal to 0.2 sine 10 power of 3 T. Okay, so T over here meaning that this B is moving, meaning that your magnetic field is moving. Okay, sebab kita ada T dekat sini. Okay, okay, maknanya different time, different value of this B. Alright. So that means these questions is referring to the transformer EMF, where in transformer EMF, your loop will be static, but your B will be moving. Okay, for that one, so we need to use the first equations of your transformer EMF, which is V EMF equals to negative N, differentiation and integrations of your flux B dot ds. Okay. So from here, you need to, it's easier for you if you divide this equation into two parts. So one will be, the first one will be you need to find what is the flux itself. And then the second one, you need to differentiate your flux. Okay. So if we look here, we divide this equation into two parts. So part one, we solve the flux first. All right. So you can see here, flux is equals to the integrations of B dot ds. And this B just now is given to you where the value is 0.2 sine 10 power of 3 T. The directions is AZ. And now, what is your ds? So ds, you go back to the figure, you can see that ds is referring to where your magnetic flux passing through. So which surface that your magnetic flux passing through. Okay, so you can see here, the surface is this circle. So this circle, the area of this circle, so we need to know what is ds, right? So the circle of this area, we know that it is rho d phi d rho. Okay, so rho d phi d rho. Or when we integrate, it will be pi r squared. Okay, r is the radius, so we can have pi r squared. Okay, so we integrate from here, we know that a rho d rho integrate will have rho squared over 2, and then d phi will be 2 pi, so cancel out both 2, and then we will get pi r squared. Okay, so this is the integrations punya value. So from here, you substitute what is your radius. Okay, in this case, we are using r. So r is equals to 0.1 because the radius of this circle is 0.1. And the final answer for this flux is 2 times 10 power of 3 pi sine 10 power of 3 t. Okay. All right, so we have this 10 power of 3 because again, oh no, kejap ya. Alright. Okay, so bila kita squarekan dia, dia akan ada 10 power of 3. Okay. Alright, so we solve the yes.
Untuk total area tu, Yaro Diro DV tu kan. So, tentu nak kena buat calculation penuh je untuk dapatkan pi r squared tu.
Calculation penuh meaning?
Kena ada letak limit Kena kira macam ni ke? 0 2 pi 0 r.
Ya, betul. That's why kamu dapat pi r squared.
Tak, maksud saya kena buat full equation lah. Macam mana dia boleh dapat pi r squared tu. Dia terus skip, tak payah buat calculation tau. Tulis je ni.
Either way pun boleh. So kalau kamu nak masukkan dekat sini siap-siap 0 until 0.1 pun boleh, ataupun later kamu masukkan r equals to 0.1 pun boleh. Sama je. Okay? Saya faham maksud kamu dekat integration ni tadi, rho di rho. So we put the limit 0 until 0.1, right? And then dv is the limit is 0 until 2 pi. So kita akan dapat 2 pi untuk dv. So bila kita cancel out and everything, we should get pi times dengan 0.1 squared juga. Sama juga. Okay?
So boleh lah.
Boleh, yes.
Okay.
Alright, so we solve our flux. So the second part we need to differentiate. Okay, so assume n equals to 1 because we have only a single loop over here. So we know that n equals to 1. Alright, so we have VEMF over here is a negative d over dt times dengan flux. So your flux just now is 2 times 10 power of negative 3 pi sine 10 power of 3t. So kamu differentiatekan dia, you will get negative 10 power of 3 times dengan 2 times 10 power of 3 pi. Okay, and then this sign will be cos. Okay, bila kamu differentiatekan dia, sign will be cos, and then your final answer will be this one. So negative 2 pi cos 10 power of 3t, unit dia adalah volt. Alright. Okay, so we have this V electromotive force, and then the question want you to find ataupun to determine what is the induced current. Okay, so of course we need to use the equations of V equals to IR, and from there you find your current, which is I induced equals to VEMF divided by R. So R is given as 5 ohm just now, and this is your V. So you will get final answer for your I will be negative 1.26 cos 10 power of 3t amperes. Okay, unit amperes. Alright. So that is for example number 1. Okay, now if we look for the example number 2, for this one, we have a conducting bar. So this is what we call as a conducting bar. And this bar can slide freely along this line ataupun along this rail. Okay, this bar can slide freely. So meaning that this bar is moving. Okay, can move. Alright, so a conducting bar can slide freely over 2 conducting rails. So calculate the induced voltage. Okay, so induced voltage meaning that we need to find VEMF in the bar. Okay, so A, if the bar is stationed at Y equals to 8. Okay, so Y equals to 8 meaning that 0 sampai 8 for the Y. So 0 until 8. So Y bar ni stop at Y equals to 8, and B is 4 cos 10 power of 6t. So again we have t dekat B. Okay, so for that we need to use the transformer EMF because the bar is moving now. Okay, if we look here dekat equations of B, we have t. Okay, so T determine that this B is moving. Alright, so we need to use the equations of transformer EMF. So we have this negative N, d over dt, integrations of B dot ds. Alright, so again, we need to divide into 2 parts again. Okay, so the first part, we need to solve the flux. Okay, we need to find the flux. Alright. Okay, so B dot ds. So B is given to you, and ds is the surface. So we look back to this figure, we can see that the surface that the flux passing through, okay, so this is the flux. So the flux, kalau kamu tengok simbol, so meaning that it going up, okay, it's going up towards you. It's going up towards you. So you can see a circle with dot inside. Kalau dia cross inside, maknanya it's going away from you. Maknanya dia going inside that. Okay, ni dia going out towards you. So this is your magnetic field. Okay, so maknanya like this. So it passing this area which is x and y. So that's why your ds is equals to dx dy. Okay, we have this line over here is dy line, and the line over here is dx line. Okay, so you can see inside your figure. So this is dx line and this is dy line. So your flux passing through in this area. Okay, so it's a rectangular area. So you have your ds will be dx dy, and the directions is az. So you can see that directions of your flux is az directions. All right. So you need to integrate this. So you can see here 4 times 10 power of negative 3 cos 10 power of 6 t, and the integrations. Okay, so like Shami asked just now, we can use this value, we can include inside here ataupun we can include later. So it's either way pun boleh. Okay, so you see here it includes earlier, so 0 until 0.06 for dx. Okay, so you can see that the length of dx here daripada 0 until 0.06, and the length of y over here is from 0 until this this is 0.08. Kamu kena betulkan balik. So this is 0 until 0.8. Okay, for the y. So you can see here 0.08. Okay, so when you integrate that, you will get 0.06 times dengan 0.08 and the value of this. Okay, and then the final value for your flux will be this one. Okay, 19.2 times 10 power of negative 6 cos 10 power of 6. So again, don't forget that this dia ada ni tadi. Okay, ada milli. Alright. So don't forget to include that. We have milli inside the value of your flux. So we'll get the final answer for your flux is 19.2 times 10 power of minus 6. Okay. So when you have your flux, you can do the second part where you need to differentiate your flux. So we have VEMF equals to negative d over dt. Okay, and this is your flux. So you differentiate cos, you will get negative sign. So negative dengan negative will cancel out, and then this 10 power of 6 will move in front. So kamu darabkan this, and you will get something like this. Okay, so that is the value for your VEMF. All right, so B, the second part for your questions, this one. Now, if the bar slides at a velocity u, okay, 20 ay, and then b is 4 az. So you can see here bar 4 az. So there is no t, so maknanya bar is not moving. Alright. Okay, so for that, we need to use the equations of motional EMF. Mana dia? Okay, so here, in this case, B has no T term and the bar slides at velocity in the Y direction. So this is a motional EMF. Alright, so we need to use VEMF, which is U cross B dot DL. Okay, so this okay, so first you need to do the cross product dulu. So you can see here your cross product is U cross B. So you have your U, which is 20 AY, and then this is your B, which is 4 times 10 power of minus 3 AZ. So AY cross dengan AZ, it will be Y cross Z. So it will be AX. Okay, so that's why you have this AX. And then this one over here, you just time for both values. So you will get 80 times 10 power of minus 3. Alright, so now you need to determine what is your DL. So again, DL is referring to where the line where it cuts your magnetic ataupun magnetic flux density over here. So where is the line? Which line that cuts the magnetic field? Okay, so you can see here ataupun you can look back into your figure. You can see here, this is your bar. So which line that cuts the magnetic field? Okay, because the bar is moving like this. So the line yang dia cut is this line. Okay, dia tak cut this way tapi dia cut this way because dia moving kiri dan kanan. Okay, so maknanya line ni yang cut the magnetic field. So this line will be DX punya line. Okay, whatever line yang parallel dengan dia. So parallel dengan this bar is the DX. So that will be the line. So the line tu bukan dekat sini, dia tak cut through pergi atas bawah tapi dia cut through kiri kanan. So kiri kanan meaning that this is the line. Okay, and this line is DX punya line. Okay. So okay, so you can see here this is the line that cut through this magnetic field. So we have this X punya line, so that's why DL equals to DX. Okay, and now we need to determine what is the value of the what is the directions of this DL. So again, dalam notes tadi, the directions of DL should be the same as the directions of U cross B, your U cross B. So U cross B directions is AX. So you need to put DL equals to DX AX. Okay. Kalau directions of this U cross B is negative AX, so you need to put here negative AX. Okay. Remember that, yeah? So first kamu just cari line dia kat mana. So again, line dia adalah DX. So DX, kita tak tahu dia positive DX ataupun negative DX. So to know what is the directions of this line, so you need to look back into your cross product. So your cross product is positive AX. So your line should be positive AX. Alright? Okay, so you have that. So substitute inside your equation just now. So you have this cross product punya value dot. Okay, ni dot ni jangan tinggal So dot dengan DL. Okay, so the equation is U cross B dot DL. So you substitute all the value inside the equation. So you will get something like this. And then the next one, the integrations of this DX, okay, the length of this DX, again, inside the notes just now, we have 3 notes, kan? So inside the notes just now, you need to put the limit of the integration must be opposite the directions of your AX. Okay, must be the opposite directions of your DL and also your cross product. So if your directions of your cross product and DL is AX, so the limit will be negative direction. So how to put negative directions is by this way. Okay, so instead of 0 until 0.06, okay, kalau 0 sampai 0.06, that will be positive value, kan? So if 0.06 6 to 0, that will be negative value. Okay, so that is what it means by negative directions. So because of this, AX is positive directions. So by the Lenz's law, you need to oppose the directions of the current. So that's why you need to put negative directions for the limit. So instead of 0 to 0.06, you need to put 0.06 to 0. Okay, so you will get your final answer will be negative 4.8 millivolt. Alright, so saya ada tulis lagi kat sini. So DL is along the line where it cuts the B, okay, cuts the magnetic field, and must be the same as U cross B. The direction must be the same directions of U cross B. Alright, so when you get your DL, so do the cross product, of course do the cross product to determine the directions. Oh, patutnya ni first dulu, and then this will be the second, okay? And then we'll have this integral limit opposite the direction. So example, if the directions is AX, limit should be 0 to 0.06 to 0. So opposite the directions of AX just now, so it will be negative AX punya directions. Okay, so that's why kita ada 0.06 to 0. Alright. Okay, so we go to the third example over here. So we have this rectangular loop. Alright, shows a rectangular loop with a length of 1 meter. So panjang loop ni adalah 1 meter and the width is 0.1 meter. Okay, so width dia adalah 0.1 and the length is 1. The rectangular loop move towards the origin at the velocity of u negative 20 ay. Okay, and b dia adalah 10 YAZ. Alright, and then calculate the total electromotive force, voltage, VEMF, okay, induced in the loop, and then hence calculate the current when the coil side are at Y equals to 0.3 M and 0.4 M if given the loop resistance is R equals to 5 kilo ohm. Okay, so you have two things. One is to find the total electromotive force, and another one you need to find what is the current induced in the coil. Okay, so if you look into what parameters are given to you, you have this U and B, so of course we need to use emotional EMF. Alright, so for that, we need to use U cross B. Okay, so this figure over here just to show that which line that cutting the magnetic field. So you can see here when the loop is moving, okay, loop ni moving to the left and to the right, okay, the line that cutting the magnetic field, so you can see the magnetic field is here. So the line that cutting the magnetic field when the loop is moving is this one. So this is the line. Okay, dia move ke kiri dan ke kanan. Okay, so this is the line. Alright, so line yang sini it will stay at the same direction ataupun same point. Okay, yang move hanya yang sini saja, which is dia ke kiri dan ke kanan. So that's why this is the line that cutting the magnetic field, and this line is parallel to X. So that means DL is equals to DX. Okay. Right, so this is just to show which line that cutting the magnetic field. Okay, so we have these equations. So you have U cross B dot DL. So first find your cross product dulu. So we have U is negative 20 AY. Okay, and your B is 10Y. Alright, so we have this AY cross dengan AZ, we have this AX. Okay, positive AX. Tapi because of kita ada negatif kat sini, so kita tarik negatif tu pergi dekat AX just to show that the directions of this direction will be A. Okay, so we di kat sini A cross Z adalah positif, B is negative 200 YAX. So kita ambil negative value tu put at the direction. So it means that direction dia adalah negative AX. Okay, so you know that DL tadi adalah DX, and then we need to follow the directions of the cross product. So cross product kita tahu dia adalah negative AX, so that's why kita letak directions of this DL is negative AX. Okay, so saya tulis kat sini extra follows cross product punya directions, which is negative AX. Alright, so when you have that, you substitute this cross product and DL into the equations. So you can see here, this is your cross product, 200y negative AX, and this is your DX. And you know that DX, the limit is 0 until 1 because the length of your loop tadi, this length is 0 until 1. Okay, panjang dia adalah 1. So, okay, so 1. Right, kamu tengok sini ya. So the limit of integrations, kalau if the directions of your cross product and your line is negative AX, so your limit ni, the value of the limit should be opposite the direction, so it should be positive AX. So that's why it start from 0 until 1. Okay, dia supposed to be positive AX, so that's why dia 0 until 1. Kalau direction kat sini adalah AX sahaja, okay, kalau directions for your cross product and your DL is AX, this one the limit should be 1 until 0. Okay, sebab dia mesti opposite the direction. So kalau ni negative, this should be positive. Kalau ni positive, this should be negative. So kalau dia negative, dia adalah 1 sampai 0. Okay, so because of this value is negative, so we use 0 until 1, which is the positive directions. Okay, so saya tulis juga kat sini opposite cross directions AX, so limit 0 until 1. So you will get your final answer for your VEMF. Oh, saya lupa nak explain. Tadi we have two sections here. We have one left section and we have one right section. Because you can see here, saya lupa pula nak explain. You can see here, this is your loop. So instead of one single line yang cut the magnetic field, we have two lines that cut magnetic field. Satu line tu dekat 0.3 and another line is dekat 0.4. So these two line, so kita kena cari both. So that's why kita ada left sections, okay, and then we have the right sections. Alright, so I hope that the left section tadi you understand. So we go to the right section. So similar thing, the only is that for your B, okay, so your U cross B, but your B value will be instead of 10Y is Z, now it will 10 times dengan Y plus to plus 0.1 because now this, so before at this line B dia adalah 10Y. Okay, so B dekat this line pula plus 0.1. So we have 10Y plus 10.1. Okay, 10 times dengan Y plus 0.1. So this value is 1 when these two line is 0.1. So that's why we need to plus 0.1. Okay, so you can see here, this is your U and this is your B. So B is 10 times dengan y plus 0.1. Alright. Okay, of course you will get ax, but we have this negative value over here, so the direction will be negative ax, and then we substitute inside the equations, and you know that dl is dx sama juga, and the direction must follow the cross product directions, which is negative ax. Okay, and then from there, because of this is negative ax, the limit of your integration will be positive value. So it will be start from 0 until 1. Alright. And the final answer for your VEMF is 200Y plus 0.1 volt. So to find the total VEMF, you need to plus and yang left dengan kena tambahkan tu. Tak ada syarat. Okay. So kamu kena syarat tambahkan. So okay, tapi dia suruh cari y equals to 0.3. Kejap ya. Alright, the question want you to find 0.3 just now. Okay, calculate the current when the coils are at y 0.3 and 0.4. Okay, so if you look into the questions, calculate the total electromotive force voltage VEMF induced in the loop. So meaning that the VEMF left tadi plus dengan VEMF right. Okay, then after that baru kamu cari the current which is at y equals to 0.3 dengan 0.4. Okay, so kamu jangan kena buat satu-satu lah ikut soalan dia. So soalan dia nak kamu cari the total electromotive force dulu, second one baru cari the current. Okay, by using this value. Alright, so again here kamu kena cari total ni dulu, which is this plus dengan yang left tadi. Kamu totalkan dia, then baru kamu cari current. So this should be for current. Mana this baru cari untuk find. Ni masuk ni. Nasiblah dia suka nak masuk lagi. Okay. Will be to the English. Okay, so kamu cari total tu berapa? Okay, so it's not in point what we call here right. Dekat right tadi, you will get dah lari dah semua benda. to 4. Okay, and then you will get the final answer for it is negative 3.2 milliamperes. Okay, so boleh semua faham setakat ni? Boleh?
Okay, madam.
Okay. Alright, so this is the next one. Mana gambar? Okay, we have this figure. We have 2 sliding bar, and this is conducting rail. Of course, this sliding bar yang akan cut your magnetic field. Alright, so if you look here, this is sliding bar. So this sliding bar yang cut your magnetic field. So of course your DL will be DX. Okay, sebab dia adalah parallel to X punya line. Kan? So your DL is equals to DX. Alright, we go to the questions. Show 2 metal bar that can slide freely across pair of conducting rails, existent B, and then the velocity is U1 and the velocity of bar 2 is U2. So determine the induced voltage in the circuit if U1 equals to U2 and B is this. Okay, so if you look here, U1 equals to U2 equals to 0, meaning that it's not moving. Okay, and kamu punya B yang ada T, so should be you need to use transformer EMF. Okay, sebab B dia ada value of T. Maknanya B dia yang moving, so transformer EMF. Alright, so we go to the solutions. So you can see here U1 equals to U2 equals to 0 milli/second. So this is the equation. So you need to find what is B dot ds. So solve the first part dulu, which is you need to find the flux. So the flux is B dot ds. You know that your B is 20 sin omega t ax plus dengan 10 cos omega t az. Alright, so why we cross ataupun this part, the first part over here is equal to 0. Why is it equals to 0? You look into the directions of it. So you can see that this directions is AX. Okay. So bila when we have this dot product, okay, this is dot product. When we have this dot product, any directions for dot product, kalau direction dia adalah sama, which is AX dot dengan AX, let's say, okay, the answer will be equals to 1. Alright, so AX dot dengan AX, it will be equals to 1. But if AX dot dengan AZ, it will equals to 0. Okay, so you need to remember that for dot product, the same direction will be equals to 1, but in different direction like this, AX cross dengan AZ, so it will be equals to 0. Okay, so dia opposite dengan cross product. Cross product, bila kita AX cross dengan AY, we will get AZ. Tapi kalau AX cross dengan AX, we will get 0. Okay, dia opposite.
Dia tak ada guna-guna dengan simetri.
Tak ada. Tak ada. This one tak ada kena-mengena dengan simetri. So you can see that AX dot dengan AZ, so this one should be 0. Okay. Alright, so you cancel out the first part of this B. So you just left with this one, 10 cos omega t AZ. So when you, this is the dot product. So AZ dot product dengan AZ. So it will be equals to 1. So you just left with this. Right? And then again, the limit, you just look into the limit of your dx and the limit of your dy. So if we go, the limit of your y is 0 until 4 and limit of your x is 2 until 4. Right? So you can see over here, 2 until 4, 0 until 4. And then you will get your final answer for your flux, which is this one, 80 cos omega t. Alright, so substitute inside the equation to solve the problem. So you have these differentiations. So 80 cos omega t. So cos because kita differentiate dia, dia akan jadi negative sign. Alright, so you will get this and the final answer will be 80 omega sine omega t volt. Alright, so that is for the first part. So the second part, I think it's the motional EMF. So it's given to you, U1 is what and U2 is what. Okay. So you can see that the directions of your U1 is negative AX and the directions of U2 is positive AX. Okay, walaupun negative tu dia letak kat depan, so it still means that the directions is negative AX. Alright, so you can see here U cross B. So B tadi dia dah bagi what is the B. Okay, and this is your U. So negative 10, ini untuk bar yang number 1 So we are using this U1. So negative 10 AX cross dengan 2 AX minus 5 AZ. Okay, so you can see here, the answer is 50 negative AY. Alright, so sebab kamu tengok kat sini, negative 10 AX, kalau dia cross dengan 2 AX, like I said just now, cross product dia tak boleh sama. Bila dia sama, dia akan jadi 0. So you can see here AX cross dengan AX will be 0. So this one you need to cancel out. So we just left with this and minus 5 sahaja. So minus 10 AX cross dengan minus 5 AZ. So AX cross dengan AZ, kita akan dapat negative AY. Right? Tapi dia negatif, dia akan jadi positif kat sini. So we still have negative AY. So that's why we have 50 negative AY. Okay? Right, so the next one we need to determine what is DL. Like I said just now, DL dia adalah kenapa DL dia adalah dy over here? Sekejap ya. Which one yang dia move? Dia move ke kiri dan ke kanan. Dia move ke kiri dan ke kanan. So dia move this side and this side, right? This is conducting rail and this is Y is the bar. Okay, ni nak kena check balik. So it should be dx dy, it should be dx dl equals to, oh, now I understand. Okay, so why is it dy? Again, the rules of this motional EMF, so the line must follow what is the cross product, right? Before this, so the line must follow the cross product. So if let's say here the cross product, the direction is negative AY. Okay, so whatever yang dalam yang dia beri, so kita gunakan the final answer is negative AY. So DL must be the same as the cross product. So that's why DL dia adalah dy negative AY. Understand tak? Faham tak? Ada yang confused? Boleh? Can you follow me? Boleh? Cuba nak fahamkan. Okay, saya ulang semula. Alright, so dia ada 3 rules untuk motional EMF tadi kan. So the first one is that you need to find your cross product, U cross B. Okay, and then you will get something like this. This is contoh, the answer for your cross product. Okay, and the next rules is your DL ataupun your lines. So your line must follow whatever the directions of U cross B, the cross product. Okay, line ataupun DL must follow the directions of your cross product. Okay, so because of your cross product direction is negative AY, so Y dekat sini AY to the directions of AY, so your DL must be DY negative AY. Okay, DY negative AY. So that is the rules. So that's why dia dekat sini DY negative AY. Okay. Then the third rule is that for the limits. Okay, kalau limit untuk cross product and your DL is negative AY directions, your limit must be positive direction. So that's why dia start daripada 0 until 4. Alright. Okay, saya ulang semula. Okay, so for motional EMF, you have this U cross B dot DL. Okay, there are 3 rules untuk motional motional EMF. Okay, the first one, you need to find your U cross B and you need to know what is the directions of your cross product. Okay, so let's say the directions of cross product is this one, negative AY. So the second rule, your DL must follow the directions of your cross product. So here it is negative AY, so that's why your DL will be DY AY. Dia tak bolehlah jadi DX AY, dia mesti sama DY AY. And then because of this is negative AY, so you have negative AY also over here. So DY negative AY. Alright, so dia mesti sama. Kalau dia tak sama, kamu tak boleh masukkan dia dalam equation ni. Because dot product, again dot product, dia mesti sama. Kalau tak sama, dia akan jadi 0, remember? So that's why the rules, you need to have DL must be the same as U cross B. Okay, so dia mesti sama. Alright, so kalau dia adalah AY, so sini pun ada AY. So because of that, so you need to use DY. Okay, so next time kamu tak payah pening-pening cari. So just look into what is the directions of your cross product. So that will be your DL, sorry. So that will be your DL. So kalau directions of your cross product is negative AY, so your DL will be DY negative AY. Okay, and then the third rules for this motional EMF, you have these limits. Kalau the cross product and the DL's direction is negative AY, so for the Lenz's law, dia must be oppose that direction, so dia mesti jadi positive. So that's why they start daripada 0 until 4. Okay, and you will get the final answer is 200 volt. Boleh? Understand? Boleh
Ni jawapan akhir, madam?
Ni jawapan akhir untuk bar number 1. Okay, so we have second bar.
Left, right.
Yes, left, right tu. So second bar, the B is, not B, the U is different. Okay, so you look here, the U is 20AX. Alright, cross dengan 2AX minus 5AZ. So again, AX dengan AX cross, it will be equals to 0. So 20 dia cross dengan negative 5 over here. Alright, so AX cross dengan AZ akan jadi negative AY. Tapi sebab dia ada negative kat sini, dia akan jadi positive AY. So you will get answer 100 AY. So because of this is AY, your DL will be DY AY. Sama Dia mesti sama. Kalau tidak nanti dia akan equals to 0. So DY AY. And then you look here, this directions of your cross product and your line is positive AY, so your limit must be negative. So because of that, it will start at 4 and end at 0. 4 until 0 sebab dia kena opposite this direction. So this is positive, so this is negative direction. So 4 until 0. So you will get a final answer for VEMF equals to minus 400 volt. And then you need to find the total. Kamu just cari dia total dia. So you will get the final answer is negative 200 volt. Okay. Alright. So this is the next one is a straight wire. Example 5. Dengan kamu ada kelas ya lepas ni? Example 5. Okay, example 5 dengan example 7, it's a bit difficult sikit. For this one, you can see here, this one you need to use, because if you look here, example 5, show a straight wire carrying a current of 10 amperes, a metal rod of 30 cm, so this is the metal rod, move at a constant velocity of U5AZ. So dia dah bagi kamu U ni, maknanya dia adalah motional EMF. But dia tak bagi kamu magnetic field. The B tu dia tak bagi. So kamu kena cari B. So how to find B is for this one. So you need to use the Ampere's law. So you can see here, kamu kena cari B dulu. So you can see here, this is your line and this is your rod. So bila line kamu like that, it will produce this magnetic field surrounding your line current. Okay. And dia akan go to the rod. So what is your B? B is just you need to find it by using the Ampere's law to I enclose. Alright, so you know that DL of your B, which is this way, will be rho d phi. Okay, kan dia akan buat satu bulatan. So this line over here is rho d phi. So rho d phi, bila kamu integrate, you will get 2 pi rho. Okay, and equals to I. I enclose, untuk line current, I enclose dia adalah I. Right, remember before this? So I enclose dia adalah I. So you will get your H is like this. And B is just mu naught I over 2 pi rho. So then kamu substitutekan inside the equations. So you will get this U is 5AZ cross dengan A phi. So kamu punya ni A phi because this direction is A phi punya directions. Alright. So AZ cross dengan A phi, you will get negative A rho. Okay. And then substitute inside the equations. Again, because of this is negative A rho, so of course your line will be D rho negative A rho. It follows macam tadi saya cakap, dia akan ikut what is the directions of your cross product, so negative A rho. And then because of this is negative direction, so of course your limit will be positive, so it start from 0.1 until 0.4. Alright, so you will get your final answer of this. Okay. And then example 6 is practice exercise. So this kamu kena buat sendiri dulu. So example 7, so it is a bit similar with yang tadi tu. Cuma the only thing is that you need to choose whether to use this Ampere's law ataupun using biosavart. So either tu memang boleh guna untuk both. Tapi yang mana much more easier. So I think it's better for you untuk gunakan dua-dua sekali. Contoh macam yang soalan 5 tadi tu. Instead of gunakan Ampere's law, you can also use biosavart law. So for this equation, we are using Biot-Savart law. So just to show the difference. Okay. So again, it's given to you U, tapi dia tak bagi kamu B. So kamu kena cari. So from this, you can see that this is the line current. Okay. And it will produce this magnetic field along the line. Okay, surrounding the line. Okay, and then this B yang kamu kena cari. So you can see here. So we use a Biot-Savart law. So for this one, you know that you need to use this H I dl cross R over 4 pi R cube. So you need to find what is your R. Okay, from the line, you draw a straight line from the line to the point of interest. R, sebab kamu nak cari dekat sini kan, whatever inside B inside the loop. Okay, so just take one single line from your line current towards the point over here. So that will be your R. And then R will be ZAZ plus YAY. So going up will be ZAZ. Going to the right will be YAY. And you will get your R will be this one. And DL is referring to your current. So this is your DL. DL will be DZAZ. All right, and you substitute inside the equation and you will get your final answer for B is this one. Okay, so negative mu naught I over 2 pi Y. Alright, so this one, this equation sama juga kalau kamu gunakan untuk yang tadi. Untuk example 5 tadi, sama je. Kalau kamu try buat, guna Biot-Savart law for that example 5, you will get the same answer. Okay, so again, you have your U and you have your B. So this is your U and this is your B. So using cross product, AY cross dengan AX, you will get negative AZ. So because of this, we have this negative value over here. So that's why your AZ will be positive directions. All right, and then you substitute inside the equations. Of course, you need to know that you have the loop. Okay, dia ada line belah kiri and ada line belah kanan. So left and right. So you need to find for both. Alright, so AZ direction, so your DL will be DZAZ, and then because of this is positive direction, so your limit will be negative. So that's why 0.1 until 0. Okay, and then your final value for your V EMF left is this one. Alright, so now we go to the right side. So you know that equation untuk B tadi, mu naught I over 2 pi Y sahaja. Tapi because of this is untuk right punya line. So that's why you need to add Y plus 0.1. Jadi kalau kita tengok balik. Okay, tadi kita ambil line yang kat sini. Okay, now kita ambil line yang kat sini. So this line over here, kamu kena add 10 cm. So 0.1 meter. So that's why, okay, we have here your B will be Y plus 0.1. Okay, again the same step. AY cross dengan AX. Ada negative value over here. So you will get positive AZ. And then because of this is positive AZ, your DL should be the same. So DZAZ, positive directions. And because of this positive direction, your limit will be negative direction. So should be 0. Okay, and you will get your final answer for your right side is this one. These two, left and right. Okay, so boleh and then this is the last part, that the summarize of your equations in the final forms. So we have this Maxwell equation, static, electric and magnetic field. Okay, so this defined inside electrostatic and magnetostatic. So we have this at Gauss law, and then we have this dekat Ampere's law. Alright. And then we have this Maxwell equations for time varying. Okay. And this is at Gauss law. Okay, ni yang kita ada tadi. And this is also dekat Ampere's. Alright, so just remember Maxwell equation, we have two. One is static punya version and another one time varying punya versions. Okay. So for that, itu saja. And then please do this tutorial. Tak payah buat the definitions and everything, yang calculation saja. Macam yang ni, C. And then we have this is at C juga. Alright. And we have this D. Okay, buat yang calculation saja. So C dengan D. Oh, dia mesti ada dua. C dengan D. Okay. So just do C and D for all tutorials ya. Nanti kita discuss, kita tengok as usual untuk kita punya tutorial next week on Monday. Okay, so if you have any questions on this tutorial, please do ask me. Okay, tanya saya. So I will try to help you. Alright? Okay, so thank you all. Kita jumpa on Monday.
Baik, madam.
Alright, so kalau tak faham, please tanya ya.
Okay.
Go through back the video tadi. I think a few of you mesti still confused lagi, but please go through the video. Saya akan upload. Selalunya kita akan dapat balik dalam petang. So malam ni lah kalau saya dapat, nanti saya akan uploadkan. Alright?
Baik, madam.
Alright, so thank you all. Assalamualaikum.
Thank you, madam.
Waalaikumsalam.
Assalamualaikum.
Thank you.
Salam,
Madam.
Madam.